Hey everyone, and welcome. Today we're diving into what is honestly the backbone of any efficient program, data structures. We talk a lot about algorithms, the steps to solve a problem, but how we arrange our data before an algorithm even gets to it can be the difference between an app that flies and one that just crawls. So let's dive in and see how getting organized is really the secret sauce.
Okay, hold on a second. I get that an algorithm is just a list of steps, right? A to B to C. So why does the arrangement of the data matter at all? Isn't the computer just going to look through everything anyway?
That's the perfect question, because it really gets to the core of how computers see the world. You or I can walk into a messy room and spot a red book on a cluttered shelf almost instantly. Our brains are just wired for that kind of pattern recognition. A computer, though, it just sees a massive jumble of ones and zeros. It has no intuition. For an algorithm to work its magic to find anything efficiently, that data has to be laid out for it perfectly.
All right, that makes sense. So where do we start? What are the most basic, fundamental ways to just hold a bunch of stuff together? Like if I have a list of products in a database table, what's the programming equivalent?
Exactly. So a great place to start is with three common ones. First up, you've got a set. Think of a set as a bag, where everything inside has to be unique, no duplicates allowed. It's super fast for just checking, hey, is this item in here, or for cleaning up duplicates. Then there's the list, which is probably what most people think of first. It's your all-purpose, ordered collection. You can add things, remove things, change things. It's super flexible. And last, we have the tuple. It's kind of like a list, but with one huge difference. Once you create it, you can't change it. It's immutable. That makes it really fast and safe for data that you absolutely do not want to be altered by accident.
And here's the kicker. Especially for anyone who's worked with databases, trying to find a specific item in a list is almost exactly like running a query on a database table that has no index. It's a full table scan. Imagine you have 1,000,000 items in that list. To find just one, the computer has to start at the very beginning and check every single one until it hopefully finds what it's looking for. Talk about slow.
Okay, so a list is bad for searching. Got it. But what about times when you're not searching for some random thing in the middle? What if the whole point is about the order that things go in and come out?
Perfect question. That leads us to two really important structures that are all about order. First, there's the stack. It's last in, first out, or LIFO. The best way to picture this is a stack of pancakes. You add a new pancake to the top of the stack, and when you're ready to eat, you take one from the top, right? Then you have the queue. This is first in, first out, or FIFO, and this is just like a line at a coffee shop. The first person to get in line is the first person to be served. Simple as that.
Right, so stacks and queues are awesome for managing tasks in a specific order, but they don't help us with that big, slow search problem we talked about earlier. We're still stuck with that needle in a haystack issue. Right, that bull table scan is a total performance nightmare. So there has to be a better way, right? How do we build something that lets us just jump straight to the data we need without checking everything else?
Oh, there absolutely is. And the answer is a beautiful thing called a dictionary, or you might hear it called the hash map. The whole idea is that instead of just a line of items, you store everything in key value pairs. So when we want the value for pink, we don't have to scan anything. We just ask the dictionary, hey, what's at pink? And boom, we get our answer back, like instantly.
This is a total game changer. Now, it feels like magic, but it's not. It's an incredibly clever computer science concept called hashing. So let's pull back the curtain and see how this magic actually works. Okay, this is the part that always gets me. What is the secret sauce here? How can the computer possibly know the exact location of the data without, actually searching for it?
The secret is a brilliant data structure called a hash table, and the definition really says it all. A hash table is all about creating an index of keys that lets an algorithm predict where the data is. No more searching, it's all about calculation.
Okay, so here's how it breaks down. First, you take your key, in our case, the word pink. Second, you run that key through a special algorithm called a hash function. Think of it like a blender for data. Third, that function spits out a number, which is basically the direct memory address. It's like a super specific ZIM code for your data. And finally, the computer uses that address to jump straight to the location and grab the value. No scanning needed.
And in the world of computer science, this incredible efficiency has a name. We call it O of 1, or constant time complexity. That one basically means it takes just one operation, one step to find your data. It doesn't matter if you have 10 items or 10 million items. The lookup time stays the same. It's constant, and that is incredibly powerful.
Okay, wait a second. A key that gets turned into a direct address to avoid a full scan? Hang on. This sounds exactly like how a database index works. Am I on the right track here?
You absolutely nailed it. That is the core connection. A database index is, for all intents and purposes, built on this very principle. The entire reason indexes exist is to get as close as possible to that O of 1 search time, to find the row you need in one shot, instead of scanning millions. Really, the hash table is one of the fundamental concepts that makes the high-speed databases we rely on every day even possible.
So, let's just make this crystal clear, because this is the big takeaway. When you run a search on a table with no index, you're essentially doing a list search. That's a full table scan. But when you search using an index, you're doing the equivalent of a dictionary lookup. You're doing a hash lookup. It's the difference between walking a marathon and teleporting. All right, so let's quickly recap what we've covered. First and foremost, the data structure you pick is everything. It dictates your algorithm's speed. Next, lists are simple and useful, but for searching, they're painfully slow. Remember, stacks and queues are your best friends when the order of operations is key. Fourth, dictionaries are the heroes of search. They use hash tables to give you that magical O of 1 instant access. And finally, and this is the big one, this whole concept is the engine behind database indexing.
So that leaves us with one final, big question to think about. We've just seen how one small change in thinking, from a list to a dictionary, can create a mind-boggling leap in performance. And it really makes you wonder, if choosing the right data structure is this critical for speed, what other massive performance secrets are hiding out there just waiting for us in plain sight?
And that's it for this explainer. If this helped you connect some dots, do us a favor and hit like, share, and subscribe for more deep dives into the tech that powers our digital world. Thanks so much for watching.